Howdy, AP PreCal, it's Ms. Kosh. I am back doing Unit 2, multiple choice for Mr. Passwater, and we'll see how this goes. So, residuals, oh dear. This was the first year I've ever taught that, and I haven't looked at it in months. So, if I'm wrong, will you comment nicely down below, or maybe I should stop and go look this up and make sure I know what I'm talking about. But, okay, basically, what I remember from residuals is that if the residual plot has a pattern to it, then it wasn't a good plot. That we didn't pick a good model. So, let's see. Linear regression was used to create a model. I see a pattern, so this tells me that the linear regression was a bad choice. The figure shows a graph of the residuals of the linear. What are the following statements about the linear regression is true? It's appropriate. I think it's not appropriate because the residuals do not show a linear pattern. The linear regression, here we go. The linear regression model is not appropriate because the residuals show a clear pattern. If I'm wrong, will you comment down below? There might be an answer key to this at some point, or if you disagree with me, let me know why you disagree, and we'll kind of go from there. I see another pattern here on this one. I mean, it's a little less of a pattern, but let's see. A regression model was created for the data. Oh, this data looks exponential. The quadratic regression model was used, and the model is appropriate. No. A quadratic, okay, hang on. The residual plot for the model is given to the right. Which of the following statements about the regression model is best? Well, this doesn't look quadratic, and this looks to me mostly like a pattern. I mean, this one guy up here doesn't really fit the pattern. An exponential regression model. I'll be curious to see what they say the answer to this one is. The quadratic regression model was used and the model is not appropriate. That might be the case because this graph looks exponential. This model, this residual plot looks like it has a pattern. So it would tell us that whatever they used was not appropriate. So with the exponential regression model, if it was used, I would think that it should be appropriate and therefore the values should be scattered. So I'm with 75% certitude picking that answer. This gives you something to comment about down below. See if you agree with me, and we'll go from there. Yeah, this is interesting. Maybe I should stop and go review residuals. It was interesting to me that they added this to our pre-cal curriculum. In 24 years of teaching, I've never taught residuals. So he believes the data set displayed exponential growth. He used the set of data to create an exponential regression model. The residual plot, okay, this to me has no pattern. Based on the residual plot has no apparent pattern, so the exponential model was appropriate. I think that's correct. No apparent, so the exponential, this is wrong. I don't think it displays a pattern, so I think we're looking at A right there for that one. A set of data was used to create a linear, quadratic, and an exponential regression model. The residual plots were, for the three models are shown above. This is the linear. This looks like it has a pattern. This is the quadratic. It looks like it has a pattern. This does not seem to have much of a pattern. I think it is exponential. This is linear. This is quadratic. This is exponential. This is logarithmic. I think our answer choice is C. Okay. The data, a set of data in a linear regression model constructed for the data shown in the figure. Which of the following is the best estimate for the residual point for point P? Oh. Oh, dang it. The residual, is it expected minus actual or actual minus expected? That's how far are we from this line? That doesn't look too far. It's not 3. I'll take that one off the table. Because if we were 3 units away, this would be a distance of that. Okay, that's 3 units, even though, is it 1.5? That would be about half of that. It doesn't seem like 1.5. I think it's 0.5, and I think it's below the line, so I think it's negative. But you know what? I saw something about residuals. Oh, and I closed that file. Sorry, you get to pause or watch me on double speed till I get back to where I was supposed to be. The residuals. No, that's okay. Sorry. No, that didn't help me. Hang on just a little bit longer. You're doing great. Keep on hanging on. The residual actual from the data minus the predicted. Okay, actual, so it's actual minus the predicted. And so the actual here seems to be smaller than this line. So I think it should be the actual is a smaller number minus a bigger number. I think that's going to be the negative one. Report back if you disagree with me. Comment below. Hopefully this is not a huge part of the test. So there we go. An exponential, it'll be interesting to see. They report back and they're like, all of your kids, Miss Kosh, did great on trig and they sucked on the residual stuff. Well, sorry. Okay, a little sidebar. Okay, back at it. Here we go. So this is an exponential function. The coordinates of point P are -1, 1. Which of the following statement is true about the residual of point P? Okay, so what would have happened when I plug in -1? I would have gotten 3 times, 2 to the -1 is 1/2, so this is 3/2. So, but instead I got 1. So what did we just say? We just wrote down that it's the actual minus the predicted. So here's the predicted, there's the actual. 1 minus that is going to be negative. Okay, so we want a negative, the residual is going to be negative. A negative value because the model predicts an overestimate. Yes, it's not under, because if it were under, then the actual minus the predicted would be positive. Okay, oh goodness, okay, here we go. The points P and Q are labeled. Which of the following statements is true about the model and estimates produced by the model that correspond to P and Q? Okay, they might be, okay, it looks like Q is farther away from the line than P is. Should I be doing, you know what? I'm doing this wrong, you guys. I think I should be looking at the Y values here. Okay, it's still, Q is still bigger. Sorry. The residuals have the same sign. No. One's above the line, one's below the line, so they don't have the same sign. They have opposite signs. Based on the absolute value of the residuals, there's a negative error. There's a greater error in the model with P than with Q. No, I think the Q is farther away from the line. Okay, I think it's this one. So if anybody is just an expert at all things statistical and all things residual, comment below, let me know, tell me, yes, Ms. Kosh, you were doing great, or Ms. Kosh, go back and study that again and remake this video. I might not do it, but anyway. Okay, let's get to something I'm good at. Okay, so here's our table. They're giving us f of x and g of x based on this table. Functions f and g are defined for real, so we're looking at h. Oh, okay. So h of x is equal to f of, I lied, that's a g. G of f of x. Okay, so what's h of 9? Well, h of 9 would be g of f of 9. Okay, f of 9, when I plug in 9, I get 5. So this is going to be g of 5. So when I look at 5 and look at g, I get 4. That was fun. It gave me confidence again that I know what I'm doing. Okay, so k of 3, so this one is k of 3 is going to be equal to f of g of 3. Looking up here, g of 3 is going to be 5. So this is going to be equal to f of 5. F of 5 is 8. Okay. On this one, there's some line segments. This is g. Over here, this is f. Okay. So h of 8 is going to be g of f of 8. So we're going to have an x value of 8. We're going to look at the graph of f. So 8 is a positive 1. So this is going to be equal to g of positive 1. And then g is here. G of positive 1 looks like negative 2. Okay, the next one's probably the same. I don't really want to do that. The table gives us select values here. This is our function. Oh, okay. What is the value of g of, oh, okay. This is f, this is g. Let's do g of f of 1. Well, f of 1 is equal to 1/2, so that's equal to g of 1/2. G of 1/2, if I plug in 1/2 right here, it's going to be, well, 9 to the 1/2 power is saying the square root of 9, which is 3, minus 1/2 times, so this is 3 minus half of 8 is 4. So this is negative 1, and that's an answer choice. Oh, good. Okay, So here's our two functions. So what's an expression? Okay, so f of g of x. What I can do is I can write out f, which was this. It's 4 times something squared. 4, I lied. 4 raised to the something squared. What is that something? Well, that something is now g, which is 3x. Okay, and so what would I do here? I would say this is 4 to the 9x squared. Is that an answer choice? It is. There we go. All right, here's function f and g. They want g of f of x. So we can write out g, which is something squared plus 3 times something. What is the something? The something is f that we need to plug in. So 2x minus 1, 2x minus 1. If you don't know how to square this, go back and watch my other videos. 4x squared minus 2, so minus 4x plus 1. Plus 6x minus 3. Let's combine all this together. Well, or we can eliminate the ones that don't have 4x and x cubed. Oh, you have to really mess up to get an x cubed. I'm sorry, don't do that. Okay, plus 2x minus 2. Is that an answer choice? It sure is. There we go. Okay. Oh, inverse function. Okay, so what would I do with this one? I would look and say, okay, this is... well, I should read the directions. They give us a piecewise function and consists of 2 line segments. The function g is the inverse, therefore g is equal to the inverse of f. Okay. So this is the point negative 4, 3, which tells me I need the point 3, negative 4 on my graph. So let's see, 3, negative 4 should be right here. That means this one's no good. Okay, 3, negative 4. That's 3, negative 4. That's no good. 3, negative 4. Okay, that's encouraging. 3, negative 4. That's not there. Okay, let's double check that we have other things that are correct. So I think this has to be our answer. Now this is where I'm not a nice person. I would have made more than one graph have this 3, negative 4, so you can't just use that. What's another point? This is the point negative 2, negative 1. So that means we have the point negative 1, negative 2. Negative 1, negative 2, that's encouraging. And then this was the point 2, negative 3. So the inverse, switch x and y, negative 3, 2. Negative 3, 2 is right here. So yeah, it's C. That was fun. Okay. So we have these two. The function is the inverse. So what's the domain of g? Well, the domain of g is going to be the range of f. So what's the range of f? From negative 2 to positive 3. So negative 2 to positive 3. What is the minimum value of k? Okay, so k is, oh, that's interesting. I haven't thought about it in that regard. Well, so we're going to have the point, this is the point negative 3, 4, and so my new graph is going to have the point 4, negative 3. So 4, negative 3 comes over here. And then this is the point 1, 0, so then we're going to have 0, 1, so we're going to have this point, so those two were connected. And then this is the point 5, 2, so we now have the point 2, why is this not a function? What am I doing wrong? Oh, did you catch my mistake before I did? This should be negative, my bad, okay. Ignore this. So this should be the point negative 4. No wonder. I was like, what is happening? Negative 4, negative 3. Okay, so it's this. And then we have this point is now 2. 5 is going to be up here somewhere. So we're connecting. Okay, so what's the minimum value of k? The minimum value is the smallest x value becomes the smallest y value. Can we always say that? Well, we switch our x and our y's. If the minimum value of the function k is going to be the smallest y value, which means it came from the smallest x value. I did more work than I needed to. Negative 3. I've never thought of asking a question that way. That's very clever. It almost caught me. Okay. I think I got the right answer. If I didn't, comment below. The table gives us the increasing function, and I apologize if I'm wrong, but you know, I'm good, but I'm not perfect. Especially with a headache. Okay, if I have f to the negative 1 of 4, what that's telling me is that we're looking for x. We're looking for the x value that gives me a y of 4. Okay, so when I see a y of 4, I want the x value, and that's at 6. So it's not a 4 here to get a 3. What this is, yeah, they're switching around. So what did I just say? The answer should be 6. Okie dokie. The table gives values for an invertible function. Okay, invertible functions, both of those can have, their inverses are functions. What's the value of, okay, g of 4 is 7. So we're looking for the inverse of f of 7. So we're looking for the x value when the y value of f is 7. So the y value of f is 7, so this is 2. I think all of these behave in a similar way. Let's jump to this one because it's a little trickier perhaps. Okay, so the inverse of this we just said was 2. So this is going to be equal to the inverse of g of 2. So this is when y is 2 for g. What's the x? The x is 7. That's a complicated way to ask these questions. That's pretty good. Okay, the function h is increasing for all values. Okay, so it's increasing for all values. The graph is concave up for all values. Let the function k be the inverse. Okay, so here's what I imagine. If it's concave up and increasing, it's going to look something like that. Which of the following statements is true? If I switch x and y, what I have done is I have reflected it over the line y equals x. So, or it's going to look, here's also how I'm thinking about this. If this could be something, this could be an exponential function, which means that its inverse, maybe I should call this h and k or whatever, but the inverse of that would be the log base 2 of x, and a log function looks something like this. Okay, so then if it's increasing and concave up, then we're going to have something, this is increasing and concave down. Can we say that all the time? Okay, let's see. I think my reasoning is solid, but I hate to generalize it for, I was looking at the specific scenarios of an exponential and a logarithmic function, and so I want to make sure I can generalize to those particular situations. There might be other graphs that are increasing and concave up, but not exponential. Yeah, I bet there are, but okay. Increasing and the graph is, okay, so this is, sorry. Okay, let's think about this. If it's increasing, that means its average rate of change is positive, and it's concave up, that means its average rate of change is increasing. Okay, so does that tell me if it's positive? Okay, well, here's an interesting thing. If I have a function and then I take it, so then the average rate of change, let's think about this for a second. The average rate of change is equal to the change in y's, that's a delta. The change in y over the change in x. Well, if I take the inverse of my function, then my x's become my y's and my y's become my x's. Well, this, if by flipping this over, if this was positive, flipping it over, it's still going to be positive. So if it's increasing, it's still going to be increasing, it won't be decreasing. Okay, I feel good about that. So now let's see, if the graph is, if this is increasing, if the average rate of change is increasing, then my change in, this is going to be, these values are increasing. Does that tell me? Well, I think it has to be concave down because of my example. Comment below if you found a better way to explain this one, or if you disagree with my answer. This multiple choice is going to slow us down and make us think. So study, 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 practice, 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 and let me know how I can help you. How long? Oh yeah, we've gotten to a stopping point. I will come back for more. See you in a minute.